All right, so we have seen so far that generating a decision tree from a set of examples simply requires picking an important attribute and then splitting the examples based on the values of that attribute. So that allows us to create subtrees. And if the attribute we have chosen is good, we will see that it will actually eliminate some of the examples, as we have seen in the case of patrons here. Out of the 12 examples, we are left with only 6 to deal with. So we're going to choose another important attribute to do the splitting and so on. So eventually we will end up with a tree that is as short as possible, and that will allow us to actually decide if we receive a new input, how do we map it to one of the correct output. This is what exactly the algorithm referred to as choosing the most important attribute. Okay, so if you have examples that consist of a mixture of different possible outcomes, the thing to do is to choose an important attribute and then split the examples, so thereby creating subtrees, and then you continue the process. So the question now left for us to answer is, how do we choose this important attribute that we shall use for the splitting? This is what we are going to learn next. So choosing an attribute continues. Now, to select the most important attribute to use to split a node, we use a very important information attribute called information gain. Now, information gain, to compute it, we need to first compute another attribute which is called entropy. So these are the two terms we are going to learn first before we can be able to know how to choose this important attribute. All right, so we're going to start with entropy. What does it actually mean? Now, entropy is a measure of randomness in data values. That is the amount of disorder in the data values. It is defined as this. So the entropy, which is denoted as h of x of a distribution x, where x consists of elements x1, x2, x3, and so on, is defined as follows. Hx is minus the summation of the probabilities of each xi times log to base 2 of that same probability. So probability of x1 times log to base 2 of x1 plus probability of x2 times log to base 2 of x2, and so on, until the number of possible values that you have in the distribution of x. So this is what we are going to use. So for example, if you have your x to be equal to patrons, as we saw that the values for patrons consist of none, sum, and full. So to compute the entropy for patrons, we will say probability of none times its log, so log of the probability of none, plus probability of sum. And of course we can compute the probability of sum. It simply means how many examples from those that are patrons, those examples from the column of patron, as we calculated in the previous example, how many of them are a sum out of the total? That will give us the probability of sum. Okay, times log to base 2 of the same probability. plus we do the same for full. Okay, the probability of full means how many of the examples are full, and then times the log to base 2 of the same probability. We will take example to see this is done in terms of computation, but this is definition of entropy. Now, in case you have binary attributes, so actually the elements of X are just true and false, then the formula can be simplified like this, because then we have just trues and false. So we're going to have probability of P equal to true times the log of P, okay, then minus 1 minus P. As we know, if the probability of true is P, then the probability of false is 1 minus P. So we compute the probability of false, which is going to be 1 minus P, multiplied by a log to base 2 of the same probability. So the formula reduces to this simple expression. Now, in general, the entropy of X is maximized. That is, the degree of randomness of a variable X is maximized when all the Xi values are equal, whereas it is minimized when one element is 1 and the rest of the elements are 0. Okay, because of course, remember, entropy is the degree of randomness. So if all elements are equally likely, then the randomness is the maximum at that time. But if we are certain one of the elements is 1, so it is really certain, then there is no randomness at all. And therefore, we'll see that the entropy in that case is going to be 0. Let's take an example of tossing a coin, for example. Okay, suppose you have a fair coin, so that when you tossed it, you are equally likely to get tail or head. Okay, so in that case, the degree of randomness is higher if the coin is fair. Okay, so you can see, just to try the formula for the entropy. In that case, the probability of head is 1 out of 2. Okay, so we just say 1 over 2 times log of 1 over 2. Okay, remember the log is to base 2, minus the probability of tail. Okay, so this is the probability of head is half. The probability of tail will also be half. So this 1 minus P is also half. So you have half times probability of half. So if you add these two halves, actually what you will end up with is minus log of to base 2 of half. Okay, but log to base 2 of half is actually log to base 2 of half is the same as 2 to the power minus 1. So if you take minus 1 and multiply it with this minus 1, you will end up with actually log to base 2 of 2. And we know log to base 2 of 2 is actually 1. Okay, so you can see therefore that if the coin is fair and you have a probability of getting the head to be half and the tail to also be half, we will have the entropy Hx to be equal to 1. So that is the maximum entropy. Okay, now suppose the coin is not fair. Suppose the coin is unfair, so that we are certain whenever we toss it, it is going to show head or it is going to show tail. So in that case, the probability of let's say head, assuming it's going to show head all the time. So the probability of head is going to be 1 actually. Okay, and the probability of tail is going to be 0. So you can see that if you apply the formula, we will have minus 1, because that's the probability of head, times log to base 2 of 1. Okay, minus 0 times probability of 0, or times log to base 2 of 0. So anyway, this is going to be 0, but this is also going to be 0 because log of 1 is 0. Log of 1 to base 2 is 0. So eventually what will end up is 0. If you are certain that you're going to get head, you're going to get 0. So you can see the entropy in that case is going to be 0. Similarly, if you are certain you're going to get tail all the time, again, the probability is going to be 1, and you see the entropy is 0. So this is basically the idea of entropy. It gives you the degree of randomness, and it is maximum if all outcomes are equally likely. If all outcomes are equally likely. Right, so we're going to use this idea to now define what is called information gain. Okay, so having computed the entropy or the entropies of the individual items, the next step is to compute the information gain. And actually it is this information gain that will tell us which attribute is the most important attribute. So far we have seen how to compute the entropy of a particular attribute. The next thing we need to learn is how to compute the information gain if that attribute has been used to split the set of examples. Now for that we need two entropies. Let us denote by HP the entropy of class distribution for a particular node, or if you like, for a particular attribute. That is to say, the entropy of that attribute before splitting the node. Okay, so let HP denote the entropy of the attribute before splitting the node. Then we compute the entropy of the same node, but given that the examples are split, or the data set is split based on that attribute. Okay, so this is what we call conditional entropy. The entropy after splitting the data based on attribute A. This is normally computed by actually taking the weighted average entropy of conditional class distribution based on the individual data values for that particular attribute. So you're going to partition it based on the values and compute the individual entropies of each subgroup, and then take a weighted average. We will see this in an example in a moment. And then you sum up these averages to get this entropy after splitting. Okay, now once you have these two entropies, then you can compute the information gain. Okay, so information gain, normally denoted by IG, from splitting a node A, is defined as the entropy before splitting the data according to attribute A minus the entropy after splitting the A. Okay, remember, entropy is the degree of randomness. So what is the degree of randomness before the splitting? And now what is the degree of randomness after splitting? So if you remove the degree of randomness after splitting from the degree of randomness before, then you will have what is called information gain. All right, yeah. So basically we're going to subtract this from this, and that gives us the information gain. Now, in choosing the most important attribute to use to split the data, the simple rule is compute the information gain of each attribute and choose the one that has the highest value. Okay, so at each internal node, split a node with the largest information gain, or equivalently, the node with the smallest conditional entropy. Okay, because we are subtracting this from the entropy before. So the smaller value we subtract, the bigger information gain we are going to have. All right. Now, one thing to note is that by definition, the conditional entropy cannot be greater than the entropy before the splitting. Okay, and therefore the information gain will always be non-negative. If it is not positive, then it will be 0, but never negative. Okay, now this will make sense when we take an example. So to see how to compute the information gain, let us go back to our examples of these two attributes, patrons and type, and compute their information gain based on what we have just explained in the last slide. So first we note that for each of these attributes, if you count the number of positives and the number of negatives before we do the splitting, is the same. And the number of positive P is the same as the number of negatives, and is equal to 6. Okay, so we have, before we split, equal number of positives and equal number of negatives. Okay, this is before we choose any of the attributes. So if you compute the entropy, therefore, the entropy before splitting, okay, it is going to be entropy of 6 out of 12, and entropy of for positive, and 6 out of 12 for negative. And obviously, because they are equal, each of them is half, we will have maximum entropy in this case, and it's going to be 1 bit. Okay, right. So this is the entropy before. The next question is, what is the entropy after the splitting? So for patrons, it's going to be 1, which is the entropy before the splitting, minus the weighted average of the entropies after splitting. So this is the one you need to pay attention to see how we compute it. Okay, now so for patrons, we remember we have 3 different values for the attribute. We have none, we have some, and we have full. And if you look, we have completely negative. And in the 2 examples that we get in the known branch, they are both negative. All right, so basically we are going to have the entropy of 0, 1. In other words, there are no positive. It's completely negative. Okay, and out of the total, because remember we're going to weight these entropies according to the proportion of elements we have in each branch. So we have 2 out of the 12 for this particular branch. So 2 over 12 times entropy of 0, 1. 0 because there are no positive in this group. They are all negative, so 0, 1. Plus, we compute the weighted entropy of sum. So for sum, because there are 4 of them out of the total 12, the weight is going to be 4 out of 12 times the entropy of that group. Again, as you can see, this is a pure splitting. All of them are positive, 0 negatives. So we're going to have, again, this going to be 0. It's going to be the lowest entropy. Okay, so it's going to be H of 1, 0. 1 being is all positive and no negative at all. Okay, plus the entropy of full, the weighted entropy of full. So weighted means we have to multiply the entropy by the proportion of values that are in this branch, and it's going to be 6 out of the 12 times the entropy of that group. Now here we have values for both true, which is 2 out of the 6. Okay, notice that this 2 is computed out of the total of full, not out of the total for that attribute, just the values. So 2 out of 6 are positive and 4 out of 6 are negative. Now if you notice, for this particular splitting using patron, basically this is going to be 0, because this is going to be, the entropy is going to be 0, so 0 times 2 over 12 is going to be 0. Similarly, this is going to be 0. So actually all you have is this term here. So now you have to go and compute this, and as we learned, this is going to be so of course you're going to multiply by 6 out of 12, so it's going to be minus 2 over 6 times log of 2 base 2, log 2 base 2 of 2 over 6 minus 4 over 6 log 2 base 2 of 4 over 6. Okay, so this, if you calculate, will actually give you this value that you are seeing here, 0.541. So this is how to compute the information gain. Let's do the same for the other attribute type and see what we have. So again, there is no difference in terms of the entropy before the splitting. It is still 1. But now the entropy after splitting is going to be different, because as you can see, we don't have a pure group in any of this. They are all consistent of the same number of positive and negatives. Okay, so we're going to weight them according to the number of elements in each subgroup. So we have 2 out of the 12 in the first group, so 2 over 12 times the entropy of the values. Okay, so because the elements are equal number, actually this is going to be 1. Okay, similarly when you go to the second one, Italian, again is 1, 1. So the number of positives and number of negatives are equal. So this again is going to be 1. Okay, similarly this is going to be 1 for the Thai, and then for the burger the entropy is going to be 1. So essentially what you have actually is 2 out of 12 plus 2 out of 12 plus 4 out of 12 plus 4 out of 12. If you add all of these, you're going to get 1, and 1 minus 1 is equal to 0. Okay, so this is very important because it tells you if you choose this attribute to do the splitting, you're going to get no information at all. The information gain is 0. This is why choosing the type as an attribute to do the splitting is going to be a bad choice. You don't gain any information at all. Okay, so the rule actually is whenever you are splitting, you should choose the attribute that gives you the highest information gain. And although we have done it for only two of the attributes, if you do for the other attributes, you will actually find that in this sample, patrons give the highest information gain. So actually it's the first attribute to use to do the splitting. All right, so this is basically how to split the a node when you are constructing the decision tree. And the final decision tree that you get, if you follow that algorithm, is what you have seen here. This was the original tree which was generated by the authors, not following any particular algorithm. Okay, and this is the one that is generated if we follow the algorithm that we have discussed, the decision tree algorithm. So, and you can see this tree is much shorter in terms of height, and we can decide if we are giving any input using very few steps whether the customer is going to wait or is going to leave. And this is basically how to apply the algorithm to construct decision tree. Now, performance measure. The next thing to learn after knowing how to construct decision tree using the algorithm that we have seen is how do you measure the performance of your algorithm. Okay, remember to measure the performance, we have to use the test data and see whether the tree that we have generated will approximate to the true function that is supposed to map the input to the output. Okay, so the question here is, how do we know that the H that we have generated, the hypothesis, is approximately equal to the true function? And the only way to do that actually is by experimentation. So it says here performance is measured by applying the learned hypothesis, which is the model, on test data and measuring the accuracy. All right. According to the authors, they started off with 100 examples. And then they started with a training set of size 1. And they increased the training set by 1 each time until it reaches 99. So they are basically partitioning the data between the training and test data, and then using the tree they obtain, they apply the test data and compare the result obtained with the expected output, and they measure that with this graph. And for each partition, say for each size, so size 1, size 2, size 3, and so on until size 99, they actually repeated the process of randomly splitting the data between the training and the test set 20 times, and then take the average of the 20 trials, the average results of the 20 trials. So based on this, they plotted this graph, as you can see, from when the training size was 1, 2, 3, and so on until the training size was 99. So the curve shows that as the training set size grows, the accuracy of the hypothesis increases. The maximum they got was 95%. All right, so this is basically how to measure the performance of the hypothesis. you partition the data into training and test, and then you apply your test data on the algorithm, compare the result that you get with the expected result, and you can compute a plot like this to see how accurate it is. So 95% is pretty good approximation. Now, before we conclude the lecture, we take another example, which is the example of creditworthiness. So here we have a set of examples, the same example that I showed you earlier in the lecture, but this time we are dealing with creditworthiness. So let's say a bank is trying to determine whether to give a loan to a particular customer. So they are trying to base their decision on the information they have regarding how previous customers behave, whether they actually pay back the loan or not. They found that it depends on 3 attributes. So the first attribute is refund. The customers, did they actually refund the loan or not? Okay, the other attribute is marital status. So some of them are single, some of them are married, and some of them are divorced. Okay, and the third one is their income. Okay, so these are numeric values, as you can see. So the last attribute here is cheat, meaning this customer, is he a cheat or not? So no, if he is not a cheat, he will actually return the loan, or yes, if he is a cheat. So this is the training data. So this is a sample decision tree that can be generated from this data. So if you choose refund as the first attribute, obviously if the customer refund the loan, definitely he is not a cheat. Okay, so this is a clear answer. We're going to have no. As you can see here, if you look at refund, anytime refund is yes, the cheat is always going to be no. If refund is yes, cheat is going to be no. Yes, no. Yeah, so this is what we can see from this data. Okay, so we can group the data first according to refund. If he is refunding, then definitely he is not a cheat. Now, what if he doesn't refund? Then we have to look at the other attributes. Probably the next attribute to check, and you can do this by actually computing the information gain to see which next attribute is better to use to split the data. Marital status, suppose we use that, then you will see that among the remaining attributes for which the refund is no, okay, we have we will see that among those that are married, again, they are always not cheaters. All right, so let us look. If you look at not refund, is he married? Then cheating is going to be no. Okay, and similarly for here, refund is no, married, cheating is equal to no. So this seems to be a good attribute to use to split the data. Okay, now what if he is not married? Then he could be single or divorced. Okay, so in that case we choose the income to see whether we can distribute the rest of the data. And you can see in this case the customers that have an income less than 80,000, according to this data, they are actually not cheaters. It is those that earn more than 80,000 that are actually cheaters. Okay, yeah, so again, this is just an example. If you really want to apply the algorithm that we have learned in this class, you need to first of all compute the information gain for each of these three attributes, and then use the one that has the highest information gain to do the splitting. All right, you will see that refund actually will be the best one, and then you go further to check the remaining two, and you continue the splitting like that until you are able to split the data and form this final tree. So this is the model. So once you have your model, the next thing is to test your data to see what class are you going to be able to allocate this remaining values. Okay, so for example, suppose you have an example where refund is no, married is yes, and taxable income is 80,000. The question is, what is going to be his class? Is it going to be a cheat or not? So according to the original decision tree that we generated, we go through the sequence, looking at each of the attributes. So in terms of refund, the answer is no. He doesn't refund. So we go therefore to check the marital status. All right. Now for the marital status, he is married. Okay. So according to the tree, we should go to the right. All right. And clearly, without even checking the income, the tree is able to help us to say, no, this is not a cheater. At least based on the data we have, all married people are good people. So the answer is for the class we're gonna assign no. Okay, this is the idea. Now, so in summary, in this lecture, we learned that learning takes many forms depending on the nature of the agent, the component to be improved, and the available feedback. Okay, we have seen there is supervised learning, unsupervised learning, and reinforcement learning. If the available feedback provides the correct answer, for example, inputs, then the learning problem is called supervised learning. And in that case, the task is to learn the function h that will allow you to map each input x, which is not inside your training data, to a corresponding value y. And we have learned that supervised learning can be considered as two types depending on the type of output. If you have discrete valued as your output, then the learning is called classification. Okay, whereas if the output is continuous, like a real number, then it is called regression. And a simple example of classification method is the learning decision tree, which we have learned in this lecture. And we learned that learning decision trees can represent all Boolean functions. So they are very expressive. However, they can be expensive at the same time. And therefore we needed a more efficient method, and we saw that information gain heuristic actually provide an efficient method for finding a simple consistent decision tree. Okay, and the performance of a learning algorithm is measured by the learning curve, which shows the prediction accuracy on the test set as a function of the training set size. So this brings us to the end of this lecture. Thank you very much.